Hi everyone, today I will talk about our paper, Receiver-Driven Congestion Control for InfiniBand. Designed for lossless and low-latency communications, InfiniBand has become the leading standards-based interconnect technology in high-performance computing. To guarantee no packet loss under normal operations, IB provides credit-based link-level flow control. The side effect of link-level flow control is congestion spreading, where all packets passing the branches of the congestion tree, no matter whether they are contributors or not, must wait for credits, which is also called headline blocking. This increases queuing delay and damages the completion time of applications. To deal with the congestion spreading problem, a congestion control mechanism, IBCC, is proposed in the IB specification. In IBCC, switches are responsible for detecting and signaling congestion. When the queue length exceeds the selected threshold and there are available credits, it is identified as a route of congestion. Then the switch notifies the receive side by FECN bit notification. The CA is responsible for rate regulation. Once a congestion notification packet is received, the sending rate is regulated with a fixed step according to a CCT table. So IBCC usually requires multiple round-trip times to converge to the desired rate after the congestion is detected. Nowadays, HPC systems are increasingly being used to run varied workloads, including data analytics, scientific simulation, and storage. Besides, jobs in HPC systems typically execute concurrently and contend for shared resources, such as networks, infrastructure, and file systems. So, MPI messages generated by communication-intensive applications and long-lived traffic of I/O-intensive applications may traverse the same switching fabric. The resultant traffic patterns are increasingly diverse. So the coexisting diverse traffic imposes great challenges to congestion control for InfiniBand. In this paper, we conduct fine-grained experiments to re-examine IBCC under the typical scenario. The traffic is a mixture of large and small messages. Concretely, H1 and H2 will send large messages forming long-lived flow F1 and F2, sending to R1 and R2 respectively. Assume that at time 0, F1 and F2 converge to their fair share rates. After a while, H3 to H17 will send small messages to R2 at the same time. These small messages cannot be controlled by the end-to-end congestion control, and these small messages form concurrent bursts, which will last for about 1 millisecond. In this scenario, and after the burst launching, congestion will happen at the port P0. The overall throughput performance is shown in these figures. Ideally, F1 does not contribute to the congestion at port P0, so it should not be throttled during burst launching. F2 is congested and should be reduced the rate properly. The results show that without congestion control, the victim flow F1 has the same throughput as the congested flow F2. With IBCC, F1 still has throughput loss for about 1.5 milliseconds, and the link from P2 to P1 is underutilized during this period of time. We draw several insights from above observations. First, periodical updated credits may confuse congestion detection. We find that port P2 may still receive some available credits periodically. Thus, in IBCC, F1 is partially identified as congested during the short period and is mistakenly throttled. Second, the sluggish rate adjustment of end-to-end IBCC mismatches the fast half-by-half flow control. The sending rate of F1 and F2 is decreased gradually because IBCC can only adjust the sending rate step by step. However, link-level credit-based flow control works half by half, so it reacts faster than end-to-end IBCC. The figures shows the real sending rate and the rate calculated by congestion control algorithm. For example, the real sending rate of F1 is dominated by the link-level flow control for about 0.9 milliseconds. Third, we find that in IBCC, the rate decrease process is often interrupted by the frequent rate increase operation. That is, the congestion unaware rate increase may contradict with the rate decrease process, which makes parameter tuning tough in IBCC. Motivated by above insights, we propose a new receiver-driven congestion control named RRCC. In RRCC, the CA is responsible for congestion identification and congestion notification. At the sender CA, it is in charge of the rate regulation. The switches are only responsible for detecting congestion and marking packets. The first key idea is receiver-driven congestion identification. In RRCC, the receiver side CA utilizes the feature of packet marking pattern to distinguish between the congested flows and weakening flows. In detail, for congested flows, all packets will pass through the congestion route and are marked with FECN bit, while for weakening flows, only fractional packets may have available credits to send out and may be marked with the FECN bit. The second key idea is receiver-driven rate regulation. We should decrease the rate of congested flows rapidly to the proper rate, rather than in the fashion of step by step. In fact, the receiving rate is the maximum rate that the congested flow can pass through the bottleneck link. This principle is effective under typical scenarios, including endpoint congestion, in-network congestion, and coexisting multiple congestion points scenario. In detail, the receiver side CA is responsible for calculating receiving rate by counting the number of receiving packets. After identifying whether the flow is congested or not, the CA will generate congestion notification packets to the send side to guide rate decrease or increase explicitly. The receiving rate information is also page-backed in the CNP packets. On the other hand, the send side CA conducts simple yet effective rate adjustment rules for different flows. When the CA receives a CNP packet with the BECN bit set indicating that the flow is congested, it will perform rate decrease according to the receiving rate, page-backed in the CNP packet. When the CA receives a CNP packet without BECN bit set, indicating that the flow is uncongested or weakening flow, it will directly perform the rate increase following averaging principle. Now we evaluate RCC in simulations. We first evaluate RCC in the typical scenario. The overall throughput and the detailed rate of each flow are shown in the figures. The congested flow F2 is throttled to the proper rate rapidly, and flow F1 quickly occupies the available bandwidth in 0.3 milliseconds. And the link level flow control does not dominate the real sending rate during burst launching. In a word, RRCC can achieve fast congestion elimination and has short convergence time. Then we vary the arriving interval of burst to introduce different extent of congestion. The results show that as the arriving interval decreases, the throughput of weakening flow F1 and the link utilization is not affected in RRCC, combining with IBCC and without congestion control. We also conduct large-scale simulations to evaluate IRCC under workload with mixed MPI and IO messages. Under various settings, IRCC has better average and tail latency than IBCC. This is because IRCC can regulate the sending rate in one control loop as soon as congestion is detected. The accumulated buffer can be drained rapidly, thus reduces current delay for MPI messages. As for the link utilization, it is challenging for IBCC to achieve high link utilization and low latency for MPI messages simultaneously due to its independent rate increase and rate decrease process. Last, we evaluate other properties of IRCC. Results show that IRCC has good fairness property, and the overhead of generating CMP packets in IRCC is tolerable. To conclude, we investigate IBCC performance on the typical mixed traffic scenario and propose IRCC. IRCC can achieve much better message latency with fewer parameter tuning and is compatible with commodity InfiniBand switches. Okay, that's all, and thank you for your listening.